Have you ever wondered what happens when a star, much bigger than our sun, ends its life? You see, not all stars share the same fate. The ultimate destiny of a star is determined by a crucial factor: its mass. Stars, just like us, go through a life cycle. Born from a dense cloud of gas and dust, they spend most of their lives fusing hydrogen into helium in their cores. But what happens when the hydrogen runs out? For stars with a mass less than 8 times that of our sun, they puff up into red giants and shed their outer layers, leaving behind a white dwarf. However, stars more massive than this don't go out quietly. Their cores collapse under the immense gravitational pressure, triggering a supernova explosion, a cosmic spectacle of epic proportions. Well, the death of such a star gives rise to what we call a neutron star, one of the most extreme and fascinating objects in our universe. So, how does a star transform into a neutron star? Well, it all begins when a star exhausts its nuclear fuel. This isn't an abrupt process, mind you. It happens over millions, if not billions, of years. As the star burns through its hydrogen, then helium, then heavier and heavier elements, all the way up to iron. But even a star can't create energy from iron. Once a star's core has turned to iron, it can no longer sustain nuclear fusion. This is the point where the star's life takes a dramatic and violent turn. With the cessation of nuclear fusion, the star loses its primary source of energy, and gravity takes the upper hand. The iron core collapses under its own weight, shrinking from thousands of miles across to just a few miles in mere seconds. This rapid collapse releases an enormous amount of energy, resulting in a supernova explosion. Now here's where our neutron star begins to take shape. The core of the star, now crushed under unimaginable pressure, undergoes a dramatic transformation. Protons and electrons are squeezed together so tightly that they merge to form neutrons. This results in a core so dense that a mere teaspoon of its material would weigh about 1 billion tons on Earth. This newly formed core, composed almost entirely of neutrons, is what we call a neutron star. The birth of a neutron star, however, is not a quiet affair. The star's outer layers, propelled by the supernova explosion, are flung into space, leaving behind a brilliant nebula. The neutron star, meanwhile, spins rapidly, often emitting beams of radiation from its poles. If these beams sweep across Earth, we see the neutron star as a pulsar, a celestial lighthouse blinking in the dark vastness of space. And that, in a nutshell, is how a neutron star is born, from the ashes of a dying star. Now that we know how a neutron star is born, let's delve deeper into the key aspects of these cosmic wonders. Neutron stars, despite being the remnants of deceased massive stars, are fascinating objects that continue to confound and captivate astronomers. They're astoundingly small for stars, with diameters of about 20 kilometers, or roughly the size of a small city. Yet, they pack a punch in terms of density. Imagine cramming a mass greater than that of the sun into such a compact space. The density of a neutron star is so immense that a teaspoonful of its matter would weigh about 1 billion tons on Earth. These stars are not only dense, but they also boast magnetic fields that are 1 trillion times stronger than Earth's. This magnetic field, coupled with the star's rapid rotation, creates a beacon of radio waves that sweeps across the cosmos like the beam of a lighthouse. When this beam intersects with Earth, we perceive a regular pulse of radiation, leading to the star's classification as a pulsar. The conditions on a neutron star are nothing short of intense. The gravitational pull is about 200 billion times stronger than Earth's gravity. If you were to drop an object from a height of 1 meter on a neutron star, it would hit the surface in a microsecond, reaching speeds of up to 7 million kilometers per hour. As for the temperatures, newly born neutron stars can reach up to 1 million degrees Kelvin, cooling down over millions of years. For comparison, the core of our sun only reaches about 15 million degrees Kelvin. So even in their cooled state, neutron stars are hot enough to melt any material we know. Despite their small size, neutron stars are truly some of the most powerful and intriguing objects in the cosmos. They're a testament to the unfathomable extremes and wonders that lie beyond our earthly perception, waiting to be discovered and understood.